So, hello everyone. My name is Adi, and I'm a PhD student at the Electrical Engineering Department at Princeton University. I'm doing computer architecture, and I'm advised by Professor David Wenslav. Now, one of his early pieces of advice that he told me is that as a PhD researcher in a really applied field like computer architecture, computer systems, or network and security, for example, you have a lot of competition coming in from industry. So if you're going to think about problems that will take 5 or 6 years from now, so if you're competing with industry, so someone from like Eitan's group is going to come and steal your thunder. So someone's going to solve that problem within 5 years or 6 years, because a PhD takes 5 or 6 years. So in order to make the best of your own PhD and your research, you need to think about the problems 10 and 20 years from now. And that's not trivial, but it's really worthwhile because you can cut yourself from the shackles of existing technology and try to really think ahead. So this is what we're kind of trying to do with this work here. We're going to present a high-level descriptions of specialized architectures. What are specialized architectures? What motivated them? What might be impeding them? And perhaps some way that we present of overcoming their possible future difficulties. So let's start. Moore's Law. We all know, a lot of us know about Moore's Law. It has been with industry for over 50 years now. And it says eventually that, in a nutshell, that transistors are going to shrink at a rate that you'll be able to cram twice as many transistors for a given chip, and it will double itself roughly every 2 years. Now, the gains from these are quite extraordinary. So if you compare an Intel processor from 1970 and a contemporary Intel processor, the performance went up by 700 times. The price per transistor went down by 60,000 times, and a given transistor can do the same computation using 90,000 times less energy. So there are not, I'll go ahead and say there are not a lot of fields in human invention that were able to get this much magnitude in evolution and throughout that period of time sustainably. But unfortunately, this party is going to be over soon, because contemporary predictions by the ITRS predict that in 2021, we will not be able to make any smaller transistors for various reasons: energetic, economic, and so on and so forth. So we need to find a way to improve existing computations. And what people currently do. So future architectures shift towards what we call domain-specific computing. So basically the idea says that we're going to give up on a general purpose computation model. We will have specialized hardware accelerators which are tailored to conduct specific computations. So you won't have a given hardware that will run your word processor and your internet browser. You'll be able to have smaller pieces of hardware that are tailored for specific computation patterns, and this trend is being fueled by the emergence of those killer apps like graph processing, video compression, file compression, and everybody's favorite buzzword, deep learning. So there's a lot of traction that is being gained in recent years. You see that Google has their tensor processing unit. Intel has their Xeon and FPGA framework that they recently introduced. NVIDIA has spent $3 billion on developing a new architecture called Volta, which is tailored to run high-performance computing applications. And Microsoft has their reconfigurable fabric running on Bing. So a lot of money, a lot of traction, and this trend is really gaining a lot of gains. And the gains are indeed staggering, but this is probably the main point I want to get across here. So let's look at the premise of these specialized accelerators. So the idea is that we're not getting any more transistors. Moore's Law is ending. So we're not going to get any more transistors under a given budget. So let's just tweak and optimize the ones that we have. Now, is that a sustainable approach? So thinking about it, if we have a given problem and we have a fixed budget, we cannot infinitely improve ourselves and tailor this specific computation to a given hardware, and we're going to be ending up in a point where which hardware and software and computation are really, really optimized to a near optimum point, and we will not be able to optimize twice better for the next 50 years and so on and so forth. So we hit what we coined the term a specialization wall, because we architects, we love walls. So this is the wall that we're going to hit. And this is probably the point where we're going to see in like 10 or 20 years. So how can we overcome these walls? So generally, we look at this slide, and this graph basically shows us that application performance, well, is projected to go on steadily. We see that there are more accelerators that are integrated in high-performance computers to compensate for this lack of scalability in transistors per chip. But somewhere, I guess, around here in this graph, we're going to hit the specialization wall. So what we need to think about is to find maybe a future curve of something that will continue scaling. And for that, we need to know that we have memory and storage devices that continue scaling, and all contemporary projection still predict that they have a steady 20-30% annual growth rate and scaling of the ability to store more bits per given memory for 20 or 30 years. So this is worth thinking about. So architects think about, okay, so we think about memory systems. Okay, memory is much, much slower than the processors. Of course, it's going to be much slower than specific accelerator tailored to conduct specific computations, but there is a recent growing emergence in what we call non-volatile memory technologies. For example, spin torque RAMs, resistive RAMs, phase change memories, and so on and so forth. So compared to these traditional technologies like DRAM and SRAM, they scale better, they have higher energy efficiency, they have higher performance. So we would like to ask ourselves, can we use these new memory technologies to trade, basically to compensate for the lack of scalability that is imposed by us by transistors? So in order to do that, let's look at data centers as a case study. So modern data centers like Google and Facebook serve billions and billions of requests every day. So these computations that are carried out in these data centers introduce rates of high energy that is being wasted and high heat rates that is needed, to dissipate these rates. So don't let those ambient blue lights fool you when you see those pictures in data center. In reality, it's more like this. So essentially, look at this statistic. In 2013, the amount of energy needed by US data center is 91 billion kilowatts hours. That is the amount of power needed to light up all of New York's households twice for 2 years. So definitely data centers need to savor every bit of energy and to conduct the most energy efficient computation possible, because gains are phenomenal, electrical bills go down, and so on and so forth. So they are a natural target for accelerators. And a lot of these examples that I told about earlier are examples of accelerators that are being embedded in data centers. So one interesting insight that we can look at data centers is that they perform redundant computation because of popularity. You have popular results or popular websites in your search engines. You have popular videos. If you have, for example, you want to do some trip across some sort of map. So there are popular routes. There are popular online purchases on Amazon, and so on and so forth. So these, while I won't get into much details, these correspond to a power law that is called Zipf's law that was originally applied to linguistics in 1929, and basically says that there is exponential power laws between different popular items. And it was interestingly shown to apply also for web traffic, although it was shown like 80 years later after this law was first formulated. So that's one source of redundancy that can be saved in data centers. Now, this next source is that we have video compression. So video compression is pretty popular. Why? And what is the motivation? So in 2015, if you look at YouTube, so the YouTube servers were basically getting uploads of 400 hours of video every minute. So there's a lot of data, there's a lot of videos coming in, and we need to compress them. So video compression accelerators are super crucial, they're super useful, and we might need to see how we can integrate them. So interestingly enough, video compression algorithms exploit the redundancy of what's called macro blocks in video. So we can see that if we look at a video, we can see that there are blocks that are being recurred again and again because there are static parts in your video. So once you start constructing this video and you start doing all sorts of motion estimation and motion compensation algorithms on your video, you're bound to do some redundant computation because this is the inherent natures that compression is actually performed. So these computation results should be reused. Now what it all boils down is some way that for us to use memory to compensate for the lack of scaling and transistor-dependent computations. So we're using a technique that is called memoization, one possible techniques of many to use memory to compensate for computation. So if, in a general concept is you have tables that store computations, and instead of re-executing that computation again, you'll just fetch it from the memory. So let's look at a really basic example. We have the computation unit that computes a quad function. So it gets 20, so 20 by 20 is 400. Then we saved at 20 in this table. We have 4 by 4 is 16. 600 by 600 is 36,000. Now we run in 20 again. So instead of computing it through our accelerator, we just fetch it from the memory. So this is essentially memoization. So we formulated what is called a compute reuse architecture. So in order for us to develop this memoization scheme, we need to have something that we coined the 3 C's of memoization. First of all, we need correctness, because not every computation, it will be correct to memoize it. Why? Because there are all sorts of constraints on global state and side effects, which memoization is really prone to errors from. So we want to preserve the original program semantics. So what is this property is called referential transparency, and it says eventually, in a nutshell, that the same computation should always produce the same result, whether it is fetched from the processing unit or from the memory. So we must preserve the original program semantics. The second C is constrained storage, because if our input is really random and it's really uniformly distributed, so we're saving the inputs as keys to the table, and we'll have tables that can grow for trillions and trillions of entries, and it won't be feasible to implement using existing memory technologies, and it won't be cost-worthy. And the last one is in fact cost-worthy, that kind of connects to the previous one, is that we need to look at the given accelerator that we're trying to memoize, the given computation unit, and the costs of executing these computation units must be larger for us, must be larger than the cost that it takes us to store, lookup, and fetch results in order for memoization to be cost-worthy. And luckily for us, in terms of memoization, if we look at a general accelerator, a loosely coupled accelerator from a processor, this is the model that we're looking at a loosely coupled accelerator, it means that you have the accelerator core here and you have the CPU or the general purpose processor there, and they have distinct memory addresses. So what these distinct memory addresses and distinct memory spaces do is they basically, all input and output communication is explicitly done in software using DMA transfers. So basically what it gives us, that there is a clear distinction between the input, the output, and the execution, and it essentially gives us a way to evaluate and to have The hard part of memoization, which is the correctness, which is not always trivial to do by software, it's given to us by design. So we developed the scheme around that. We have a unit that does the hashing and looks over DMA. We have a unit that constructs pointer, and we have a table that uses a general non-volatile memory technology. So finally, let's talk about our evaluation. We evaluated some common case of benchmarks that are and common uses in their data centers. And for each workload as baseline, we looked at, we did a design space exploration of tailoring a core around for a given RTL for every specific task, because we want to simulate an accelerator that is really, really highly tailored to a specific task. And finally, we implemented we looked at different aspects using different memory technologies, resistive RAM, spin torque transfer RAM, and phase change memory, and gains were eventually staggering. I'm going it through a highlight because I don't have much time, and this is currently work in progress. So, final intakes from what we have learned today. So, specialized hardware is awesome. Accelerators are great, but their gains might not be scalable for the next 50 years. We need to find ways to compensate for this lack of scalability in the future, and we need to find new technologies that scale in order to embed them in the accelerators. So while memory is currently slower, the new memory technologies that scale much better might be really good candidates to compensate for these transistors. So we look today at memoization, which is one technique that allows us to gain from using memory to compensate for the lack of scaling in transistors. So we compensated by memory. So this is one technique. It's not infallible. You can poke holes in it. It fits for several cases. It might not be a silver bullet, but neither do accelerators. So we need to explore future ways of integrating memories into accelerators, and this is also work that we're currently doing right now. So we want to eventually, our ultimate goals is to minimize transistor dependencies in specialized architectures or architectures in general. And finally, a good rule for in general in life, if you want to accelerate, please don't accelerate into a wall. Thank you. Questions? Yes.
Where do you position this versus the micron automaton?
Where do we, what?
Where do you position this versus the micron automaton?
The micron automaton?
Automata processor by Micron.
Yeah, the in-memory.
It's a stack 3D.
Oh,
DRAM
processing
with
in memory?
Yes,
Yeah,
yes.
So processing in memory in general, so how is this compared to processing in memory? So that was the question. So if you have a processing in memory accelerators, they're trying to mitigate a different problem. So they're trying to mitigate the memory wall. So they might have better gains, but they're addressing the fact that memory is much slower than computations. They're bringing memory and computation closer. They're integrating new memory technologies, like you probably said. So this is what you're referring to? Okay. So comparing to them, we're addressing a different problem. We really want memory to replace computation. We don't want to bring computation closer to memory.
No, they're going to, the memory is used for the computation.
Okay. So they're they're
accelerator
implementing.
really within the memory chip, because it's a separate logic level, separate layer that has CMOS logic in it, except it's in the chip, so it has higher bandwidth to the actual DRAM array. But it is an accelerator within the memory chip. And he says, don't do the computation because of power or whatever. Instead, memorize the past results and hope that you need to do it again.
So they have some sort of accelerator or CMOS-based logic within these memory modules. So we're trying to do something opposite. We're trying to do something that does not that the computation does not depend on a number of transistors, at least not explicitly, for some cases. Okay.
Let's take more questions offline.
Thank you.